In this video, we will continue discussing the strategies of integration and work on developing our mindset for approaching integrals. If you immediately recognize a strategy or technique of integration, then you apply it to evaluate the integral. If not, we have the following list of strategies that we can mentally work through. So, is it a common antiderivative? Referring back to the table of antiderivatives we should all know. Are there any obvious algebraic simplifications that will help you out? Any obvious substitutions that jump out? Based upon the form of the integral, will one of our standard techniques work? Trigonometric integrals, is it a rational function? Is it well suited for integration by parts? Does it look like something we can apply a trig substitution to? If none of those things apply, we look for more subtle substitutions, something maybe rationalizing. Try integration by parts if possible, or think about some more advanced ways or methods of manipulating the integrand. So let's evaluate the given integral. Now, my thought process when I look at this, because of the square root of 5 plus 3x squared that appears in the denominator, I immediately jump to a trigonometric substitution. And recall, for a trigonometric substitution, if we have something like a squared plus x squared appearing in our integral, the substitution we might want to consider is x equals a tangent of theta. So what I want to do is manipulate algebraically here so that I have something like a squared plus x squared underneath the square root. That is, I want to pull a 3 out of everything in the denominator. Now, if we pull a 3 out, that would still have to be hit by the square root. And inside the square root, if we've pulled out a 3, a 5/3 plus x squared remains. And just to double check that mentally, think if you have 3 times 5/3, it's 5. 3 times x squared is 3x squared. And now we have something that we can apply a trigonometric substitution to. Our a squared is 5/3. So a should be the square root of 5/3. So we are going to go ahead and use a trigonometric substitution. X equals the square root of 5/3 tangent of theta. That means dx would be the square root of 5/3 secant squared theta d theta. Now note, the square root of 5/3 is not the nicest looking thing to work with, but remember at the same time, it really is just a number, and so we're going to treat it accordingly. So substituting that in, we have 1 over root 3 hanging around outside. Then we have in our integral a square root of 5/3, pulling that out, 1 plus tangent squared, multiplied by dx, which is the square root of 5/3 secant squared theta d theta. Now note, in the denominator, 1 plus tangent squared is secant squared. So when we take the square root, you're going to have the square root of 5/3 canceling the square root of 5/3 in the top. The square root of secant squared is going to be a secant, so that's going to cancel off one of the 2 secants that remain in the numerator. So it actually simplifies quite nicely. You have the 1 over root 3 hanging around out front, and then you're left with just the integral of secant of theta. This is something we can find in our formula sheet for common antiderivatives. The antiderivative is the natural log of the absolute value of secant theta plus tangent theta. And we are now to a familiar part of the problem. We've performed our trigonometric substitution, we've evaluated the resulting trigonometric integral, and now to get back in terms of the original variable x, we need to draw an associated right triangle. So recall, x is equal to square root 5/3 tangent theta. So x over the square root of 5/3 is tangent of theta. So we have an associated right triangle that we can draw. So tangent of theta, so x square root 5/3. By the Pythagorean theorem, the hypotenuse is going to be the square root of x squared plus the square of 5/3. So there. And note, as we've seen previously, this x squared plus 5/3 underneath the square root on the side we labeled is the term that prompted the trig substitution originally. Now we can put everything back in terms of x's. So 1 over the square root of 3, natural log, absolute value, so secant of theta. That would be square root of x squared plus 5/3 divided by the square root of 5/3 plus tangent of theta. So that would be x over the square root of 5/3, and this is all plus c. So in terms of the mindset we use to approach these problems, we immediately recognized, based upon the expression in the denominator, that this is something that should be well suited for a trigonometric substitution. Let's consider one more example in this video. So tangent cubed over cosine cubed. And an observation that we can make here is that tangent cubed over cosine cubed is really one of the familiar trigonometric integrals that we've encountered. This is equal to the integral of tangent cubed. And remember, secant is 1 over cosine, so this would be secant cubed. And whenever that power of tangent is odd, we have a method that we can use. So what we are going to do to evaluate this is go back to our method from trigonometric integrals, and I'm going to save one of the tangents, and I'm going to write this as tangent squared. And I'm also going to save one of the secants, so secant squared, and then we're going to write this as secant tangent. And the reason we do this is we're thinking that the secant tangent that we've saved is going to play the role of our du, which means we're going to want to let u be equal to secant. So we want to rewrite tangent squared in terms of secant squared. So using the Pythagorean identity, tangent squared is secant squared minus 1. So times secant squared times secant tangent. And we now perform the substitution we've indicated. We let u be equal to secant of x, so that du is secant tangent. So our integrand very conveniently becomes u squared minus 1 times u squared du, which is u to the 4th minus u squared. And each of these terms very conveniently differentiates. We have 1/5 u to the 5th minus 1/3 u cubed plus c. And our last step is to now resubstitute. Each u is going to become a secant. So 1/5 secant to the 5th minus 1/3 secant cubed plus c. So once we recognize that we have one of these familiar trigonometric integrals, we can apply the previous techniques that we've discussed.